The moment the Atlas alert hit my desk, I realized we were witnessing the birth of the third confirmed interstellar object in human history. No preamble, no philosophical detour, just the raw fact that something not from our solar system had slipped through the gravitational web of the sun and entered our cosmic backyard. I remember staring at the early data stream, watching the orbital solution converge into a clean hyperbolic trajectory. That was the giveaway. Nothing bound to the sun behaves like that unless it's being flung out, not held in. And this object, catalogued immediately as 3I Atlas, was unmistakably outbound, an immigrant from the stars. Its light curve settled into a stable rhythm, pulsing with a precision that suggested a flattened, elongated geometry. Not spherical like most asteroids, not chaotic like comets. Something more exotic, vaguely reminiscent of the infamous Oumuamua, but brighter, significantly brighter. The reflectivity patterns teased the idea of a smooth surface, or at least an unusually coherent distribution of ice and dust. Astronomers around the world, myself included, leaned in with a kind of collective scientific hunger, stable rotation, predictable brightness. A clean hyperbolic arc. That was our foundation, the quiet before the rupture. This is the moment in science when intuition whispers something is about to break. With each new observational pass, Atlas displayed an almost serene consistency. It tumbled through space with the calm confidence of an object untouched for millions, perhaps billions, of years. To me, that stability was as fascinating as any anomaly. Interstellar space is violent, filled with radiation, stray particles, gravitational tides. Yet this object had survived long enough to wander into our system with its structure intact. I began sketching rough models on a notepad, a flattened shard of primordial rock, frozen volatiles locked within, possibly coated with organic residues formed in the void between stars. That alone would make it historic. But there was something else in the early data that kept tugging at me, an oddly sharp asymmetry in the brightness curve. Too subtle to headline, too persistent to ignore. A slight dip, a lingering whisper of a face we had not yet seen. The so-called dark side. Every spinning body has one, of course, but in this case, the difference in reflectivity was almost dramatic. A darker hemisphere, a hidden past, something shielded from stellar radiation for so long that it might still carry the frozen chemistry of interstellar birth clouds. That possibility electrified me. We pointed spectrographs at it, hunting for signatures. The first spectra were disappointingly generic silicates, carbonaceous material, some reflective ices, nothing revolutionary, but every hour of new data strengthened the impression that this was not just another drifting interstellar pebble. It was too clean, too geometrically coherent, almost as if something had sculpted it, not deliberately, of course, but through some extreme natural process beyond our usual geological imagination. I remember calling a colleague at Keck Observatory and telling him, "Keep an eye on the brightness curve. If this thing changes even slightly, I want to know within minutes." He laughed, assuming I was exaggerating. But I wasn't. Something about Atlas felt volatile beneath the stillness, like a bowstring pulled taut. And then, in the days that followed, I began to notice microscopic inconsistencies in the rotational light curve. Nothing you could publish, nothing you could declare. But in science, there is an instinct, an intellectual tremor, that tells you equilibrium never lasts, especially not on an alien world shaped by physics we only partially understand. A TLAS was calm, too calm. And calm things in the cosmos have a habit of erupting. The first indication that something had gone terribly off script came from the Keck Observatory team, and it arrived as a single line of text that froze me mid-sentence. Atlas light curve has deviated. Large amplitude shift. Please confirm. I didn't need to read it twice. A stable interstellar object does not simply change its rotational brightness unless something profound, something physical, has shaken its equilibrium. I pulled up the raw feed myself, watching the once predictable oscillation warp into an erratic spike. It was unmistakable. The rotation axis had shifted, not gradually, not gracefully, violently, a spin flip. In planetary science, that word carries weight. Worlds don't casually overturn their own angular momentum. It takes force, impulse energy. And here, unfolding in the darkness beyond Mars's orbit, was an object from another star system undergoing a transformation we had no precedent for. My heart accelerated in tandem with the light curve. The brightness had surged. A new hemisphere, one we had never seen, was now facing the sun. A TLAS had turned its hidden face toward us. The Keck team scrambled to rule out errors, faulty sensors, miscalibrated filters, atmospheric distortion. Each possibility fell away like peeling bark. The data was real. I remember hearing the tremble in a junior researcher's voice as she repeated, "This is intrinsic. This is intrinsic." Her emphasis wasn't necessary. We all felt it in our bones. Interstellar visitors are rare. Interstellar visitors that change before our eyes. Those are almost mythic. When the brightness spiked again, I knew we were witnessing the exposure of something volatile. The new hemisphere was reflecting more light, suggesting fresher material, smoother surfaces, or frozen volatiles that had never been bathed in direct starlight. Whatever had happened, the flip had cracked open the object's biography. I stared at the spectrograph. For a moment, it looked like noise. Then it stabilized into a pattern. Something was shining through, a chemical voice breaking a silence of billions of years. That was when the implications hit me. Interstellar objects do not have agency. They don't decide to rotate differently. So the forces acting on Atlas had to be mechanical or physical. Yet the magnitude of the flip was too large for a simple thermal asymmetry. Even outgassing from frozen volatiles would produce a slow drift, not a sudden lurch. I picked up the phone and contacted one of the Keck leads. His first words were, "Michio, get ready. This thing just opened a door." I asked for the raw photometry. He sent it. I ran my own analysis. The signature was abrupt, an impulse applied over a period of minutes, not hours. That meant something had imparted torque in a single event. A pressure release, a pocket of volatile ice rupturing, a micro-impact with a fast-moving meteoroid. Each hypothesis felt both plausible and absurd, like trying to diagnose a patient whose anatomy you've never seen. But what captivated me most wasn't the cause, it was the result. The new rotational period stabilized quickly, but at a different angle, revealing a hemisphere whose very existence we had not been able to confirm until now. A darkened surface suddenly illuminated, a buried memory exposed. The community reacted instantly. Emergency observation windows opened around the world. Telescopes realigned. Proposals that normally took weeks received approval in hours. Scientific adrenaline had taken over. No one wanted to miss a second of this unfolding revelation. A TLAS had become a cosmic stage, and the curtains had just been ripped open. I watched the fresh brightness surge in near real time, thinking about how fragile equilibrium is in the universe. Even a primordial interstellar relic could be jolted into a new orientation by forces still unknown. But as the light grew stronger, something else sharpened inside me. An almost instinctive certainty. Whatever the cause, the flip was not the climax. It was the invitation. We had just been granted access to the dark side of an alien world, untouched since the dawn of its birth cloud, preserved by eons of cosmic night. And now, for the first time in human history, that ancient surface was staring directly into the telescopes of Earth. The real discovery was only beginning. The first spectra from the newly exposed hemisphere arrived like whispered secrets from another star system. I studied the preliminary readouts, expecting the usual cosmic suspects: water ice, carbon-rich dust, maybe faint organic residues. Instead, what emerged was a chemical fingerprint so unearthly, so pristine, that I felt the same jolt one experiences when a long-sealed vault finally cracks open. The dark side of Atlas had woken up under sunlight, and what it revealed defied every quiet assumption we held. The spectral lines were sharp, almost painfully distinct. Nitrogen ice, frozen N2N2. in a concentration I hadn't seen outside models of the colder Kuiper Belt dwarfs. Carbon monoxide ice, solid CO, stable only at temperatures found in the deep interstellar gulfs. Volatiles that should have sublimated long ago were somehow preserved beneath that shielded surface. The realization struck me with force. This hemisphere had never faced a star. Not its parent star. Not ours. Not any. It had traveled for eons in perpetual shadow, carrying within it the frozen breath of its birthplace. As the data flowed in, the contrast between the bright side and the dark side became undeniable. The illuminated hemisphere, the side we had been observing before the spin flip, was weathered, baked by solar radiation, chemically altered by the relentless assault of photons. But the newly exposed face was something else entirely. Untouched, immaculate, an interstellar time capsule. I felt my pulse quicken with each new scan. This was not a damaged relic. This was a preserved origin story. More telescopes joined the chase. The VLT, Subaru, Gemini, even smaller observatories that usually watched variable stars or exoplanet transits, all pivoted toward ATLAS. Everyone wanted a piece of the data, a glimpse into chemistry that predated our sun. It was astonishing to watch the scientific world synchronize around a single rotating shard of alien ice and dust. The spin flip had become a revelation machine. With higher resolution spectrography, the picture sharpened. The volatiles were not simply scattered. They formed layered deposits, stratified like geological rings frozen in time. Each layer represented a chapter. Regions rich in nitrogen suggesting formation in cold molecular clouds, bands of carbon monoxide hinting at rapid condensation events, pockets of other exotic ices whispering of environments we could only approximate in computer simulations. It felt as though ATLAS held the frozen architecture of a dying or birthing star system within its skin. What stunned me most was the stability of these volatiles. They hadn't sublimated even after the flip. That meant two things. First, the rotation placed them in sunlight only intermittently, and second, the thermal inertia of the surface kept them colder than we expected. The physics of this object, its density, porosity, thermal conductivity, were nothing like the asteroids and comets of our local neighborhood. It behaved like an envoy from a deeper, darker corridor of the galaxy. I leaned closer to the monitor, tracing the spectral signature of what appeared to be a faint ammonia hydrate. It was subtle, almost ghost-like, a compound so fragile that its mere survival suggested Atlas had spent most of its life in perpetual night, a hidden hemisphere sheltered through cosmic storms, radiation floods, and stellar winds. It reminded me of a whispered truth. The universe keeps its rarest secrets not in brilliance, but in shadow. The more we decoded the chemistry, the clearer the implications became. This was not simply a dark side, it was the primordial side, a preserved memory of formation, unmarred by solar processing, a chemical biography of interstellar space itself. And that's when the larger question formed in my mind, one that cut deeper than composition or temperature. How had this side remained hidden for so long? What force had kept it shielded until now? And what mechanism had finally broken that ancient symmetry? Atlas had shown us its face. But beneath the chemistry, I sensed a more profound message embedded in the ice. If we could understand why the spin flip occurred, we might uncover not only the nature of Atlas, but the story of its journey, its scars, its forces, the physics written into its core. The dark side had opened a window. Now we needed to understand who or what pushed it open. The moment the chemical puzzle of the dark side fell into place, the next question rose like a tidal force. What mechanism had the power to wrench an interstellar object into a new rotational axis so abruptly? Physics does not bend lightly. Angular momentum is sacred. To violate it requires a catalyst, one written into the laws of nature, not imagination. So I turned my attention from chemistry to dynamics, from frozen volatiles to raw force. The first hypothesis that surfaced was the one most grounded in classical comet physics: non-uniform outgassing. When volatile ices sublimate, especially exotic ones like nitrogen or carbon monoxide. They generate jets, tiny but persistent, capable of exerting thrust on a small body. I pictured Atlas drifting silently through space, sunlight slowly creeping across its surface as it approached the inner solar system. The bright side warms. Ancient deposits of volatile ice trapped just below the crust rupture, releasing gas into vacuum. That gas streams outward, producing torque. Under the right circumstances, localized heating, structural weakness, asymmetric fracture, a sudden release could trigger an impulsive rotation. But as I ran simulations, the numbers felt strained. Outgassing works wonders over long timescales, gently nudging comets and ISOs like a cosmic river. But Atlas had pivoted in minutes, not months. The magnitude of the spin flip was too large, too sudden. Outgassing alone was insufficient unless combined with something more violent, which brought me to the second hypothesis, a micrometeoroid impact, a pebble in cosmic terms, a grain of rock the size of a coin, hurtling at tens of kilometers per second. People forget that the solar system is littered with debris, and interstellar objects passing through it are exposed to high-velocity encounters. A direct hit to a weak structural point could deliver a concentrated burst of angular momentum, just enough to flip orientation without shattering the object entirely. I examined the timing, the brightness shift, the torque profile, the instantaneous change in the light curve. It matched the impulse signature of a micro-impact astonishingly well. But there was a catch. An impact energetic enough to torque an object of Atlas's size should have left visible ejecta, debris trails, dust plumes, some form of scattering signature. Yet our instruments saw none. No secondary flash, no reflective haze. It was as though the object had absorbed the impact silently without shedding mass. That inconsistency gnawed at me. So I considered the third hypothesis rooted in a subtler corner of astrophysics, the YORP effect. When an irregularly shaped body absorbs sunlight and re-radiates heat, the uneven emission creates a tiny torque over time. For small asteroids, YORP can alter rotation rates, even flip spin states, but the process is glacially slow. Years, decades, centuries. Atlas had flipped in minutes. But what if its geometry was so extreme, so razor-edged or asymmetric, that the thermal torque magnified dramatically? Even then, the timescales couldn't reconcile with what we observed. YORP was elegant theory, but wrong for this case. The more I sifted through models, the more I felt the physics pushing me toward an uncomfortable threshold, an intersection of explanations rather than a single cause. A layered object with volatile deposits aligned asymmetrically, a structurally fragile crust masking deeper cavities, a grazing micrometeoroid strike occurring precisely where stored volatiles were on the verge of sublimation, a hybrid event, a cosmic chain reaction. In that scenario, sunlight warms the bright side, pressure builds internally, stress fractures creep silently across the surface, then a micro-impact hits the weak point, a pocket of nitrogen ice fractures explosively, releasing a jet of gas that amplifies the initial torque. The object pivots violently, exposing the primordial hemisphere we had never seen. A fragile interstellar time capsule cracked open by a perfect alignment of forces. As I evaluated the combined model, something else crystallized in my mind. This spin flip wasn't merely an accident. It was a revelation mechanism written into the object's physics. Atlas had carried two faces for eons, one sculpted by time, the other preserved by darkness. And only through this rare convergence of natural forces had the hidden side been exposed to us. The cosmos had turned a page in its own book, and we were suddenly reading a chapter that was never meant to stay closed. The deeper we dug into the physics of the spin flip, the more I realized we were confronting something far larger than a single interstellar visitor. Atlas was not merely an object, it was a teacher. It had arrived in our solar system wearing two faces, one sculpted by stellar radiation, the other untouched since the dawn of its creation. And by chance, or by the ruthless orchestration of cosmic forces, It had chosen this moment, this passage through our celestial neighborhood, to reveal both. That revelation reshaped our understanding of interstellar objects in a way that felt almost philosophical. The pristine chemistry on the newly exposed hemisphere wasn't just a scientific curiosity, it was a message from a deeper corner of the galaxy. The frozen nitrogen, the carbon monoxide, the fragile ammonia hydrates, these were ingredients of star formation, relics of molecular clouds that collapse into suns and planets. They had not been erased, not heated away, not scattered. Atlas preserved them with a stubbornness that defied the violence of cosmic radiation. It was as though we were peering through a window into the era before our sun was born, into the cradle of worlds that never formed or never survived. But the implications didn't stop there. The spin flip forced us to rethink dynamics too. We once assumed interstellar objects drifted passively, ancient and inert. But Atlas reminded us that they are alive in the physical sense, dynamic, reactive, sculpted by stresses and impacts, governed by thermodynamic fragility. They are not fossils. They are actors in the cosmic play, capable of sudden transformation that changes how we search for them, how we track them, and how we interpret the fleeting glimpses we are granted. The point struck me with particular force as I reviewed the observation logs. We had nearly missed the moment of the flip. If Keck hadn't been watching at that exact hour, if sunlight hadn't triggered a volatile rupture, if a micrometeoroid hadn't struck at the perfect angle, we would have cataloged Atlas as just another faint shard of alien rock fading into the outer darkness. Billions of years of primordial chemistry would have remained hidden behind a hemisphere that never turned toward us. Science is often about precision, but sometimes it is also about luck, cosmic luck measured in millions of kilometers and fractions of a second. And that realization fueled a larger urgency. If interstellar objects can change before our eyes, then our strategies for observing them must change as well. Future surveys must anticipate volatility, rotation shifts, sudden outgassing, unpredictable behavior. The Vera C. Rubin Observatory, with its sweeping sky coverage, will be our next great sentinel. It may detect dozens or hundreds of interstellar visitors over the coming decades. Some will be inert, others may pivot or fracture or brighten unexpectedly. Each will carry secrets from distant star systems, wrapped in chemistry and motion unique to its origin. But telescopes alone are not enough. If we want answers, not guesses, not spectra, but true physical understanding, we must go to them. Not someday, soon. We need fast response missions capable of intercepting an interstellar object within months, not years. Robotic probes that can sample material before sublimation erases it. Instruments that can drill, analyze, photograph, and transmit before the visitor is lost forever in the void. Atlas made that clear. Its dark side survived billions of years, but once exposed, its volatiles fled into space within days. Information that ancient is fragile. We cannot afford hesitation. As I review the final data streams from Atlas drifting back toward the outer solar system, I feel a mixture of awe and urgency. Awe at the cosmic choreography that revealed a hemisphere untouched since birth. Urgency because we may never witness a moment like this again unless we prepare for it. Atlas flipped once. It showed us what lies beneath the shadows of interstellar time. And its message is unmistakable. The universe will reveal its secrets, but only to those who are watching, ready, and bold enough to reach out and touch the unknown before it vanishes into the dark.